Welcome. Today we examine the H2EM field propulsion system, a breakthrough in field physics that achieves what no other system can with today's technology. Extending the Griffiths cannon architecture to space-built field-governed hydrogen plasma, this system is optimized exclusively for vacuum and deep space transit. Uniquely, the H2EM field employs a direct hydrogen line from an integrated microwave cracker. No other system generates its propellant stream on demand this way. By cracking water into a hydrogen-rich stream only when thrust is demanded, we eliminate the immense mass and hazards of large-scale cryogenic hydrogen storage. This architecture allows us to reach a performance ceiling set by field physics alone, achieving peak velocities of 1 to 3% of the speed of light. The result is transit times measured in days, Jupiter and back in 10 days, Saturn in 14, Pluto in just 32. This is unprecedented. The core enabling innovation is the spine pod architecture, a universal mechanical and data bus that makes the vessel entirely mission configurable. Any pod type, propellant, reactors, or AM pods, connects via the same standardized docking collar and DIGSP registration handshake. As propellant is consumed, AIM pods physically reposition remaining pods to maintain perfect alignment with the thrust axis throughout the burn. The engine reframes hydrogen propulsion as an actively governed process, using electromagnetic field shaping to define acceleration zones. The magnetic nozzle employs REBCO high-temperature superconducting microcoils to direct the plasma exhaust without physical erosion. We operate across two distinct regimes, a high-efficiency continuous cruise and a REBCO-enabled high-thrust burst mode. In burst mode, REBCO inserts create steeper field gradients, scaling exhaust velocity proportionally to the local field intensity. When compared to conventional chemical rockets or even AFMPD thrusters, the H2EM architecture is in a class of its own. Chemical rockets are limited to an ISP of 450 seconds. H2EM burst reaches 1 million, making outer-planet return missions a reality. A 32-day round trip to Pluto is simply not feasible with any other existing or planned chemical technology. Power scaling is delivered by clip-on reactor pods. We load exactly what the mission requires with a sprint boost ceiling of 800 kilowatts. A worked example for a Pluto return shows the internal consistency of the numbers across all 32 days of the mission. The mission phases are physically consistent, validated through the Griffiths cannon 2-tier performance envelope. Our water pods serve a critical dual role: high-efficiency propellant and vital radiation shielding for the crew habitat. With its unique direct H2 line and on-demand cracking, the H2EM field is the only system buildable today that can achieve these results. It is the definitive standard for deep space transit.